Hello, welcome back to your Theory 2. Okay, so we will now proceed with your Module 3. It is now the analysis of your statically indeterminate structures still, but using different method. Okay, in your Module 2 that discusses the consistent deformation method of analyzing indeterminate structures. However, in this Module 3, we will now proceed to your slope deflection method of analyzing your statically indeterminate structures. Okay, so slope deflection method. So what is the this slope deflection method? This is a method that is introduced by George A. Money in 1915 for the analysis of indeterminate beams and frames. Okay, so this method is only applicable for analysis of indeterminate beams and indeterminate frames only. Okay, so we will not be dealing here with your trusses. So this method takes into account the bending deformations of structure leading to the derivation of the slope deflection equation. Okay, so in your slope deflection method, we will be focusing on utilizing your derived equation, which is what we call as the slope deflection method, which is this one given below. Okay, so that is your slope deflection. In your consistent deformation, we are trying to release your redundance or your extra or your excess restraints, and then solving that one and before solving for the rest, and then completely analyzing your structure. But of course, in your slope deflection, you have here already a formula given, which is derived by uh, taking into account the bending deformations. Okay, but I will not be showing you that one since that will be a little bit complicated and we do not have much time for that. Okay, so still, these are actually these deflections and then the rotations, this theta and this delta are still your rotations and deflections, which this actually is derived from your consistent deformations. Okay, this value of your this equation, okay, is derived from your consistent deformation or methods or consistent deformation method using of course your different methods of analyzing deformations. And okay, we have here now, okay, so let's discuss your slope deflection equation. So we have here your MAB. Okay, so let's say we are referring to a member of a beam or a frame. Let's consider a member. Let's call that one as member AB. Okay, so we have a member AB of a beam. The ends are point A and point B. Then if you want to get, okay, the moment AB, okay, if you say moment AB, that is the moment at end A of your member AB. So again, let's say what I did not draw here. The first point is your A, and then the second point is your B. Okay, let's imagine that there's a beam with ends A and B. So if you want to get your moment at point A in your beam, okay, so that is the internal moment, or that is the moment at point A, that is just equal to your MAB, okay? But if you want to get the moment of your point B, of your member AB still, that will just be M sub BA. Okay, let's just differentiate them by, okay, changing the arrangement of the subscript. AB means moment at A of your member AB. MBA means moment at B of your member AB still. Okay. Then what are these two? EI over L. Your EI there is of course your Young's modulus, and then of course your moment of inertia. And then your L there is of course that is the length of your member that we are considering. And then this theta A and theta B, these are your rotations at end A and B of your member AB. And then of course your delta there. Okay. You might be asking, there should be two delta, but the delta that we are considering in this equation is the relative deflection or translation, okay, between points A and B. So just like in your truss, isn't it relative? The deflection of point A with respect to point B, or deflection of point B with respect to point A. So relative deflection. And then FEM, that is plus or minus whatever the sign of your FEM. If we say FEM, that is the fixed end moment. Okay, so if you say fixed end moment, what are these? But again, if you say AB, that is the fixed end moment at point A of your member AB, FEM sub BA means that is the fixed end moment of point B of your member AB. Okay, so that is how we will read your subscript. So what again? Let's try to focus on your FEM, since of course we already know what is theta and delta, and of course the other of these variables. So let's try to proceed on what is FEM. If you'll try to consider your member, okay, and if you want to get FEM, if you say FEM, that is the fixed end moment. So it doesn't matter what type of support your member AB, okay, is attached to, we will still be considering its two end to be fixed, since we call this one a fixed end moment. I will explain you later on how that will happen, but actually it has nothing to do with the support. We only want to get the moment at the endpoints if considering it is connected on the both ends of the member is connected on fixed support. Okay, so that is why we call it a fixed end moments. It doesn't matter if this is originally, let's say this is your member AB, if that is originally simply supported, then it doesn't matter, okay? We are talking about fixed end moment. Let's try to make it fixed and then calculate the moment at this endpoint. So we call that one a fixed end moment. And okay, this is solved, of course, using your deflections and this consistent deformation method. What are these formulas here? Or what are these given here? Or formula, yes, for this computation. Okay, so PL over 8, PL over 8. So as you can see, if this is the type of loading, if you have a concentrated load exactly at the middle of the span, then that will just be a moment PL over 8, PL over 8, which is the moments are actually trying to brought back the deflection. This will be your direction of your P that will be sagging that way, or that will be deflecting that way. So your moments will try to resist that one by counteracting, so that it will bend back your beam upwards. So, okay, so this is the assumption of your fixed end moments. But of course, if your direction of this force is other way, that will go up, then of course this will be reversed. The direction of your moments will be reversed also. So again, by the way, in this method, in your in this slope deflection method, you need to consider also again a sign convention. So that we will not be changing our sign convention before on your consistent deformation. Why not make use that positive is clockwise? Okay. So later on, if you will try to use this moment at this left side of the member, fixed end moment at this left side, then that is counterclockwise. So you need to input it as a negative, and that will be clockwise, so positive. So again, that is why we have here a plus and minus. That means that is a positive or negative fixed end moment. So again, you need to stick on one sign convention. So again, if I assume that clockwise is positive, then I will be inputting that, if I need that one, in my equation as plus. If I need this, so that is a counterclockwise, so negative. Because it is important for you to fix your sign convention, because later on, if you will end up with these values of the moments MAB or MBA, you will end up there with signs plus or minus. That dictates what is the direction of your moment AB or moment BA. Okay, that is plus, then that means it is clockwise. So we need to again assume a sign convention in your FEM, and that is what we will follow in the result of your end moments. Okay, we call this one the end moments. End moments because it is the moment at the end of the members. Okay, MAB or MBA. End moments. Your FEM is the fixed end moment. Please differentiate your end moments with your fixed end moments. Your fixed end moment is just assumption to be fixed. It's just assuming that your beam is supported by fixed supports in both ends. So that is just only for the sake of calculation, but your MAB and MBA are the actual moments of your end of the members. Okay. So again, these are your FEM. So again, this is derived by other methods, just like your consistent deformation. So if you try to, of course, continue this one, try to figure out other types of loading. So I presented here the formulas of common types of loading. Okay, so the common types are, you have their concentrated load in between, concentrated load somewhere in the span. So again, AB determines the location of that, if that is not exactly at the middle. So that will just change. Okay, so these are your values. Again, so the same, let's say I will assume that clockwise is positive, counterclockwise is negative. And of course, you have here your moment at any point. So any location of that, this is your formula. A UDL, or uniform distributed load, all throughout the span. And we have more in this next slide. It is a triangular from the first end to the last end, or it is a triangular with the highest height at the middle or at the midspan, or it is just a UDL at a certain part of the total span. Okay, so these are your formulas. And again, we assume that that is the direction, or this is the direction of your fixed end moments, because again, these are assumed to be going down. But if that will be reversed, then all you need to do is reverse also your direction of your fixed end moments. So that's the time your signs will change also. Okay, so that is our formula. Theta A, theta B, delta over L, FEM, plus or minus whatever that is. So again, so this FEM could be solved at any time. All you need to do is assume that your endpoints of your member is fixed, and then solve for the moment at the ends, or that is just given by the formulas. And then what are these theta A and theta B? Okay, those are the rotations, but in slope deflection method, okay, to differentiate this from your consistent deformation, your consistent deformation uses the known deflection or known rotations to end up with the compatibility equation. Okay, so that is our consistent deformation. We will try to make use of the known deflection or rotations to end up with compatibility equations. However, in this slope deflection, we will be using the unknown deformations. Again, in your CDM, we will be using the known. If you say known, let's say that your theta A is 0, theta B is 0, delta is known to be 0, then that is where we will start with your compatibility equations. But in your slope deflection, if your theta A, theta B, and delta are the unknowns, then these are what we are going to use for your slope deflection equations. Okay, so that is our slope deflection. So okay, let's proceed. What is the procedure? So again, first is to identify the deformation at the joints of the structure that are free to rotate or translate. Okay, so identify what are these translation or rotation that are actually unknown, or if we say free to rotate or translate, it means that there is a rotation or translation that in the first place we do not know. Okay, so that is what we are going to figure out. Figure out what are these unknown rotations or translations. Then, okay, these are actually what we call as the degrees of freedom, or the other books uses the term kinematical indeterminacy, or let's just stick to degrees of freedom. So the number of unknown rotation or translation is actually the number of the degrees of freedom. Okay, we will not be focusing on the indeterminacy of the whole structure. We will focus on the rotations and translations which are unknown. So identify those one in your structure. Then those are the degrees of your freedom. So count that one, and then of course identify. Then second is compute your fixed end moment and formulate its slope deflection. So as I've said, if you'll try to go back again to our formula, you can always compute your FEM by just assuming that your end supports or endpoints are fixed, and then solve for the moments at this endpoint. And of course, since we already identified what are these unknown rotations and unknown deflection, then these are your variables actually in this equation, in your slope deflection equation. So that moment at one end of the member is in terms of the unknown deflection and rotations together with the fixed end moment at that point. And then of course on the other end, the same together with the fixed end moment at that point also. So you will end up with this slope deflection equations. Okay, so that is our second. Okay, so formulate your slope deflection equations. So you will expect there not only one, because in each end of the member there is a slope deflection equation. Okay, in each point or in each joint or in each end of the member. So let's count the number of beams or the number of members of your beams and frames then multiply it by 2 since in each member there are 2 endpoints. So that is the number of your slope deflection equations. But actually that doesn't matter. Okay, that doesn't matter. That doesn't dictate how we will solve the unknown. Since that will only contain the unknown rotations and unknown translation, but that is not the equation that we will be focusing, or that is not our K equation for the algebraic solution. And then third there, this is now your K equation, which is the equilibrium equations. Okay. So unlike in your, again, CDM, comparing it with your CDM uses your compatibility equation to solve for the redundance before using the equilibrium equations. But in your SDM, or slope deflection, we will be using right away your equilibrium equations. There is no formulation of additional compatibility equations. Of course, what we are going to use or to formulate is slope deflection equations. Then once you have this slope deflection equations, these are equations of the end moments of your members. Then we will be using that one to formulate the equilibrium equations for each joint that is free to rotate or translate. So again, the number of the equation must be equal to the number of degrees of freedom. So this is now where we will compare. Okay, the number of your unknown deformations or the number of degrees of freedom should be equal to the number of your equilibrium equations. So again, that means we will create an equilibrium equation out from each of the degrees of freedom. Okay, so I will be explaining that further on an example. So again, we will create your equilibrium equation out from each rotation. So if there are 2 rotations, 2 unknown rotations, then we will be having 2 equilibrium equations out from that. And if there is a translation or 2 or 3, then that will also be the number of equilibrium equations with that. And then summating all of that, the numbers of this total number of degree of freedom should be equal to the total number of equilibrium equations. Now, using these equilibrium equations, algebra, we can now calculate whatever is our variable. Our variable again is in your slope deflection. So again, for you not to be confused with these equations, the slope deflection, we will be using that one to formulate your equilibrium equations. Then these equilibrium equations will be our K equations to solve for the variables which we found in this slope deflection, which are rotations and translations. These are your variable. Okay, so we will be calculating that one here. So we'll try to look at the equation back. Okay, let's try to go back. Look at the equation. Your variables is, let's say, for example, only, okay, in this case, theta A, theta B, and delta. So it means we will be solving this one, and then once you have this, we will be solving now your moment at endpoints or end moments of your member. Okay. It seems like it is a little bit complicated, but once you will follow an example, then this will be simpler. Okay, so once you will calculate the unknowns, rotation, deflections, and of course, we will be using that to solve for the end moments, going back to your slope deflection. So again, in your equilibrium equations, we will be solving your rotations and deflections. Once we know that one, go back to your original slope deflection equations, then solve for that end moments. And of course, that is the equations that we'll be using, the slope deflection and the equilibrium. And once you have already your end moments, because this is what we are after here, okay, once we have this one, compute now the shear. Okay, if we have an end moment, we have also what we call as the end shears. Okay, end shears. So just like recalling your theory one, if you'll try to cut, okay, if you'll try to cut somewhere at the within the span of your beam or frame, you will expose there your member moments and then member shear. So just like this one. But this moment is already solved. The end moments, we are only focusing on the end points of your member, and the end moments is actually now solved from your equations. So what we need to solve is, for the rest, is the end shears. And then once we have that one, your member forces is already completed. Then making use of that member forces, we will be determining the support reactions. Okay, we will be solving from point or from joint to joint for us to complete and then solve all of these support reactions. Then once you have all your support reactions, you can now draw your shear and moment diagram, or you can analyze anything that you want in your indeterminate structure. Because again, once you can draw your shear and moment diagram of a beam or frame, you can actually now determine out from the shear and moment diagram the stresses and of course the deflections if you need that one, and the rotations, using of course your methods of deformations. Okay, so that is your procedure of analysis. Now let's not just focus on this, since of course I know that some cannot follow by merely understanding the words. Let's try to do examples. But okay, let's try to divide this one, since again we are talking about the applications of SDM to the frames and the beams. So let's start with your unit 1, which is in your continuous beams. Okay, continuous beams. So again, this will be applicable on continuous beams. If you say continuous beams that consist of more than one member of a beam. So for that to be considered as continuous, because of course, if you say that it's just one span, and maybe there are some cases wherein this method is applicable on single span, but there are some cases wherein this slope deflection cannot end up with an equation on a single span beam. Okay, so it depends. You will now know that one once you know how to apply your SDM in your beams. Okay, so continuous beams. So in this unit, we will be okay. These are your desired learning outcomes: to analyze your indeterminate continuous beams using your SDM, that is your slope deflection method, and then formulate slope deflection equations based on the type of supports. So before, in your CDM, that is to formulate your compatibility equations based on the type of supports. But this time, since we are using slope deflection, what we are going to formulate is the slope deflection equations. And of course, using this slope deflection, formulate also your equilibrium equations. Okay, so now let's have an example for continuous beam. So for us not to be dealing with a lot of examples, let's focus on the example that we solved using the CDM or consistent deformation, and then compare whatever is the result of this SDM with your CDM, and that should be the same. Okay, that should be the same, since this is accepted. These are of course already methods that are established for analyzing determinate structures. So that should give the same answer. Okay, so let's find out. So again, first step that we're going to do is degrees of freedom. Let's try to identify what are these degrees of freedom, or again, in other words, these are the unknown. In other terms, these are the unknown deformations. It's either rotation or deflection. So in your CDM, again, what we are going to find out is the known deformation, rotation or translation, or we call this one the deflection. So if you know that at this point theta is 0, or you know at that point delta is 0, that is where we will start your compatibility equation. That is for your CDM. But in this method, SDM, we are going to pinpoint, okay, the supports or the joints where rotations and deflections are unknowns. Okay, so that is what we are going to focus. But in this point A, we know that that is a fix, so there should be no rotation. So we will not be focusing on that. But at point C or joint C, that is simply supported, so that is free to rotate. But since that is supported, so that will not deflect. So there is no deflection, but there is a rotation. And then the same thing at point E, there is a rotation, but there is no deflection. Okay, so we have 2 degrees of freedom. It is theta C and theta E. Okay, so this is the same example as what we solved in your beams of CDM method. So the same E over EI. But since that is considered to be constant and all throughout of that, then you can just actually write it as E over or EI. And then later on that will actually cancel out. Okay, so first is to determine or identify your degrees of freedom, or these are your, in other books again, kinematical indeterminacy, or again in simpler words, these are the known, or I mean the unknown deformations. It's either rotation or deflection, but in our case there is no deflection, so these are both rotations. So these are the unknown, or these are your degrees of freedom. And then, okay, next is to calculate your fixed end moments and then formulate our slope deflection equations. These are your SDS. Okay, slope deflection equations. So first is to calculate your fixed end moments. So if you try to go back to our members, or the members, that is just actually a concentrated load in this member AB, which is 10 meters long. We have a concentrated 120 kilonewtons in between, or in the middle. The same thing in your CD, the same length and the same type of loading. So it means that the fixed end moment of this member AC, okay, that is, let's consider it as AC, since actually we do not care about that point in between. We only need to know that that is at the middle, but we do not need actually that point. So therefore, we will only have here, we will be focusing on point A, point C, and point E. So actually, as I've said a while ago, again, your type of loading and your lengths are the same. So your fixed end moment of AC and then CE are the same. However, these are, what are the formula again? Let's try to go back on the given formulas of the known loadings. So that is a concentrated load at the middle. Okay, so all you need to do is make your endpoints fixed. Then that moment there, the fixed end moment there, is just equal to PL over 8. Okay, in this left side is counterclockwise, and its right side is clockwise. So let's assume that clockwise is positive, okay, for this case. So your right side is positive, your left side is negative. So PL over 8, so that is what we are going to use for your FEM. Okay, so FEM. So AC, member AC. Your member AC, okay, your A is your left side point. And then again, as I've said, since member AC and CE has the same length and the same type of loading, so the fixed end moments are the same. Okay, let's focus on your member AC. So first point is your A, so the left point is A. FEM AC is equal, since again that is the same as your CE, so your first point is C for member CE, so that is equal to wait, this should be this should be interchanged. Okay, let me just change that one. This sign should be interchanged. This sign should be interchanged. Okay, so sorry about that. I just changed the sign, since again, in our assumption, as I've said, we will assume that clockwise is positive and counterclockwise is negative. Therefore, on the left end of this member AC and CE is counterclockwise, isn't it? That is what I've showed you a while ago, counterclockwise. So that is a negative PL over 8. Your P is 120, your L is 10, both of these members AC and CE, and all over 8, so that's a negative 150. Therefore, negative stands for counterclockwise. Okay, so we need to follow again our sign convention. Then your other end of member AC, which is your CA, okay, that is the other end C, and then for member CE, the other end is point E. So all we need to do is reverse, but the direction is reversed, but that will reflect on the sign. So this will just become positive PL over 8, so that is positive 150. So positive again is clockwise. So these are your fixed end moment. Since again, we solve this one as simple as this, since our type of loading is simple. But for a case that you have different types of loading and different lengths of your members, okay, then all you need to do is solve it separately. Okay, we only solve this one since they are identical and they have the same length. Identical type of loading and the same length. Okay. By the way, so you might be confused later on. In this example, you only have one type of loading in each member. Or in our fixed end moment formulas that are given to you, you have there only single types of loading in each member. How about if, let's say, okay, you have a concentrated load and at the same time you have UDL and at the same time you have a moment within this span. So what are you going to do for the fixed end moment? Is to break this down into part by part. Okay, so separate your concentrated, separate your moment, separate your UDL, solve your end moments one by one, and then of course, if you need your left side, all you need to do is summate all the left side fixed end moment, and whatever sign will prevail, that will be followed. And the same thing, summate all your right side. If EM, then whatever sign will prevail, that will be followed. Okay, so that is how we will deal if we have more than one type of loading on a member. Okay, however, in our case again, for this example, we have only simple, that is just PL over 8. Okay, so that is your fixed end moment. Once we already have this fixed end moment, we can now formulate or accomplish our SDE. This is your slope deflection equation. So again, that contains your degrees of freedom. These are your variables for our equations. So let's start with your, okay, so we will be using, so this is the given formula, but of course we have different subscript since we have different names of the endpoints. So our first member is AC, so your first point is A, your second point is C. So if you are, okay, so the only difference of these two ends is that if you are getting the first point A and you write that as AB, the 2 there, that twice there is the rotation at A. And if you are now going to the point B of your member AB, the twice there is your rotation at B. So that is the only difference of this. And of course your FEM. Okay, whatever the values, because it depends. Okay, so that is the only difference of your member. So if you are considering the point, then that is the twice rotation. So okay, so AC moment AC, so it means we are getting the moment at point A of your member AC. So that is 2 EI over L. Our length there is 10 meters. Then twice, so your theta at A. What is theta at A? What is rotation at A? Isn't it? I showed you that one a while ago, or I explained that that is fixed, so that should be 0. So do not write it as a variable, since of course that is already known to be 0. Substitute it already. Okay, so that it will make our equation simpler. Therefore, that will be useless. And of course, as I've explained also, there are no deflections here since these are supported points. Later on, we will go on frames, wherein if we are considering a point, even if that's a fixed point, I mean, even if that is a joint, that is not supported with respect to deflections. So that will be on frames. But for beams, at points, at the supports, at points in the support that we are considering, there are no deflections unless there is a support settlement. But we actually did not discuss that one. You can actually read about support settlements. Therefore, in this equation, we can actually neglect that delta, this minus 3 delta over L. We will be using this one on frames with sways or with deflections. So again, 2 theta A, your theta A is known to be 0 since that is a fixed. And then of course your delta there is just 0, so that is just theta C. Theta C is the other side or the other end. And we are referring to point A. So that is 1, that this is twice. So you can actually simplify this one minus. So by the way, why is it minus? Because your fixed end moment at point A, that is FEMAC, is negative. So I will be using the negative. Again, that's why we have here a plus or minus. So again, later on we will be following the signs, but we need to stick on the assumption a while ago in your FEM that clockwise is positive. But if you assume the other way in your FEM, then that should be your assumption all throughout. Okay, so for us, clockwise is positive. So that is minus. Then I will simplify. I can simplify the equation of M sub AC as EI over 5 theta C minus 150. You can simplify that one. That is just algebra. Okay. Okay, so now your MCA, that is the other end of your member AC, which is at point C. So all we need to do is interchange. Your theta C will now be twice. Your theta A is 0. So again, you can simplify, and that end fixed end moment at point C is positive. So that is plus 150. So you can simplify it this way. And then MCE, so the same, 2 over EI, your length there is the same as 10. Twice your point that we are considering, theta C, and then plus 1 of the other end, which is theta E. There is no 0 here since your theta C and theta E are actually unknown rotations. Okay, the only 0 there is the deflection, since there are no deflections. So you can simplify this one, and that is minus again, since that is the same as your AC, that is your left side. So that is counterclockwise, so negative. And this is simplified, and then MEC. So all you need again is to interchange your E and C rotations, and that is a positive since of course going here that is positive, FEMAC. Okay, so you have now your 4 is DS. Okay, so slope deflection equations. We will be using this to create your equilibrium equation where we are going to solve your theta C and theta E. So again, once we will proceed to the next step, we will now be ending up with two equations, since we have here two numbers of degrees of freedom, or 2 degrees of freedom. So there should be two equilibrium equation on the next step. So that is what we're going to do. Okay, so formulate your equilibrium equations, and then later on, once you have that, calculate the rotations and moments, since of course what we only have here is unknown rotations. So once you have your rotations again, you can go back to your SDS. These are your SDS. Okay, substitute that if that's already solved, and we will have now your end moments. And I will show you later how to use this to solve for the reactions. Okay, so how do we formulate this equilibrium equation? So as I've said, before, we will be using this unknown. Okay, we will be using these unknown rotations to create equations. So now we will be using the SDS to create your equilibrium equation. But where will we start? Okay, so all you need to do is figure out. Okay, go back to the original frame, or the problem itself. At point A, if you will try to submit a moment here, there is a moment which is actually unknown. That is one of the reaction. At point C, if you will try to take a moment here, it should be 0. Why? Because that is a simple support, isn't it? So if I will try to submit, so if I will cut my member here, so I will separate your AC and CE, you will end up with two moments. The end moment of your AC at point C, and the end moment of your CE at point C. But if you will summate these moments of your end moments of member AC and CE, they should end up 0, since there should be no excess, or there should be no resultant moment here, because there is no resisting moment, which is your reaction. There, we cannot resist that one at this point, so that should be equal to 0. The same thing at point E. Summation of moment here, which is actually just the moment or the end moment of your CE at point E. Summate that one, that should be, or equate that one to 0, since that is a simple support. So that is where we will get our equilibrium equation. Okay, so again, that is where we will get our equilibrium equation. So this one at joint C, again, summation of moment at joint C is 0, since that is simple support. So what are the moments there? What are the moments at your point C? If I will try to cut again, I will try to cut this one, that is the end moment CA. Okay, CA, and the end moment in this side, in this right side, you will have moment MCE. Okay, so these are your SDE. These are your slope deflection equations, which is your MCA and then MCE. So we will summate that one, that should end up 0. And then later on, we will go to point E. What we will just be equating to 0 is your MEC. Okay, so again, that is how we will end up with your first equilibrium equation. MCA plus MCE is equal to 0. So I will get your MCA and MCE, summate this equation, that should end up 0. So that is why we will be having your first equilibrium equation. So substitute that MCA and MCE, we will end up here now with this equation 1. Okay, you can simplify it to this point, equation 1. And then at joint E, okay, so the same thing, summation of that of moment at that point should be 0, since that is simple support. So we only have there a single moment, which is again the end moment of your member CE, which is your moment MEC, since that is at point E. So that is what we will be equating. MEC, equate that one to 0. Then you will end up with your equation 2. So this is just algebra now. You have two equations which has theta C and theta E as the unknown, or the variables. Equation 1, equation 2 solved simultaneously. You will have theta C. Okay, that's why again I'm suggesting that you should not be substituting your EI if that is constant, because later on that will just cancel out. I will show you that one. So we will now be solving your theta C and theta E in terms of EI. So theta C is 750 over 7 EI, and then theta E is negative 3000 over 7 EI. So we will take the sign. Take the sign. Okay. So these are your variables in your equilibrium equations and at the same time in your SDE equations. Okay. So go back to your SDE, substitute the theta C and theta E. So MAC, substitute your theta C, which is 750 over 7. You will end up here with negative 900 over 7. That is your moment and moments. So what are our units? Kilonewton and meter. So your moment should be kilonewton meter. Okay. So that is our unit here. So again, so I substituted the variables theta C and theta E since we already solved that one. Go back to your SDE. You will solve your end moment AC, which end up to be a negative. So if you say again negative, therefore, since again our assumption, negative is counterclockwise. So it means at point A, your moment there, this is now the actual end moments. These are not the fixed end moment. Please differentiate that one. Fixed end moment is only to be used for the solution. Okay, which we will be what we will be doing is making your both end fixed and then solve for the moment. But what we need for the support calculation is, or reaction calculation is the actual end moments. Okay, so these are the moments that will be exposed if I will try to cut that one just before the supports. So that is a negative, therefore it is counterclockwise at point A, okay, which is 900 over 7. And then MCA, substitute theta C again, you will have here positive 1350 over 7, which is positive, it is clockwise. So this is now my member AC with its end moments. And then go to your CE or member CE. This is your moment at point C. Substitute theta C, theta E. Theta E is negative. Okay. And you will end up here with negative 1350 over 7. This is your way of checking here, guys. Okay, negative is counterclockwise. If I will try to go back to my original structure, AC and CE is actually connected. That's why this is C and that is C. So if I will connect this back, you will connect that as a single beam, and C, okay, as you can see, I will consider it as a single point. So that is the same as this point. So the moment at that point should be the same, even if you will consider this AC or CE. So the moment there is 1350 over 7, which is positive. The moment here is negative 1350 over 7, which is negative, which is correct because they should be the same in value but opposite signs. Since of course, if you will try to cut or consider left side, right side, if you will try to transfer a force on the other free body diagram, you need to change direction, isn't it? That is theory 1. So again, we are correct. That is one way of checking. At a point, the two end moments on different sides should be equal in numerical value, but opposite in signs. Okay, so we are correct. That is also a way of checking that we are correct. And then now, solving your MEC, okay, substituting theta E, theta C, you will end up there with exactly 0, which is also a way of checking. Why? Your point E, you'll try to go back again. Why is it that should be 0? Because this is now the end. This is now terminated at that, and that is not connected at a fixed support. So there should be no internal moment at the last point because that is already cut, isn't it? And since that is not connected at the fixed support, then there should be no moment at all at point E. In point C, there is a moment if I will cut because that is continuous at point C. In point E, that is already terminated, so there should be no moment at point E. Again, as I've explained, it is already terminated at point A, and that is not fixed support, so there should be no moment here. Okay, and we ended up 0 with that, so we are good to go because that is true. Moment at point E should be 0. Okay, so I will not be writing there any moments. Okay, so next step, we have already your end moments, which is actually what we need for the solution and solving of your reactions. Okay, so compute end shear and determine support reaction. That is the last step that we will be doing. Compute end shear. So if you say end shears, these are your perpendicular member force on the point. Okay, perpendicular to the member. So these are, let's try to put it as V, since again, M is moment, V is shear. Okay, but if you are used with S as shear, why not? So again, the same type of subscript, I will write there V sub AC. It means that is at point A of your member AC. V sub CA, it means at point C of your member AC. Okay, so all we need to do is solve that one. And if I will try to input these moments and of course your actual loading, I will try to take a moment at A. You will solve your VCA to be positive. I mean to be going up. By the way, I already drawn the direction, so I do not need to be writing there your. I do not need to be writing there your negative. Okay, negative signs. But if you will try to make use of the value without considering the direction, then you need to consider the negative. Okay, so okay, please do not be confused with that. If you are taking into consideration the negative on your values, you should not be considering in summating the direction that you assume or your direction. But if you do not want to take into account the negative values or the negative signs, then all you need to do is in summating follow the sign conventions. Okay, so I will explain that one later. So again, summate moment at A, you will end up there with the only unknown is your VCA, and I ended up calculating that is going up. Okay, it's up to you how you will do it. And then summate at C, that will give us your V sub AC as going up also. Or if you want, since this is already solved, using summation vertical, you will end up with that. Or you can make use that as your checking. Get moment at point A, you will solve that one. Get moment at point C, you will solve this one. Now check that one by summation of vertical. That should end up with exactly 120. Okay? And the same thing will happen at your CE. Summate moment here, you will end up that to be going up. Summate moment there, you will end up there to be going up. Okay? This will not always be the case, especially if one of this moment will be reversed. That is possible. Okay? It depends on the type of loading, but for our loading, that is simply at the middle and simply going down. So this is typical directions of reactions. So again, these are your end shears. So where are we going to use these end moments and end shears? Okay, so where are we going to use now? That is now to be used to determine now your support reactions of our indeterminate. So how are we going to do that? This is your next slide. This is the member, okay? End moments and shear. End moments and shear. You have that completely. All we need to do is transfer this end shear and end moments on your supports. Because in your supports, that is where we can find your unknown reactions. Okay. So now this is at point A. So transfer that one at support A or at point A, exactly point A. So this moment is originally counterclockwise, so that will go clockwise this way. That shear is going up, this will transfer going down. So now, of course, using your equilibrium, summation vertical, summation horizontal, summation moment, you will solve the unknown reactions. Okay, so this is now the end step. Transfer your end moments to your supports and then solve for the support reactions. Okay, so let's focus on your point A. Okay, that is again what happened. The directions will change, but the same value. So summate moment at point A, I will summate moment there. So the only moment there is AC and MA, or that is the reaction. So it's up to you how you will assume, but okay, I will stick to clockwise positive. So clockwise there is MCA minus MA. You will end up with MCA or MA equals MAC, which is 900 over 7. Okay, this is the time. This is what I'm saying. A while ago, we solved that to be negative. But since I already write down or I already indicated there the direction, and in my summation here, I consider the direction for the signs, then all I need to do is use the value. Do not include the sign. But if you do not want to include or to focus on the direction in summating that one, all you need to do is add all of that. There is no minus or whatever that is. Then you need to consider the sign because that will reflect. Okay, so please, again, that should be known in your theory 1. Taking the negative sign or forgetting about the negative sign. Forget about the negative if you consider the actual direction in summating. Okay, so I consider the actual direction. That's why we have here a negative moment. Therefore, I will use a positive values. So now you will end up here, since again these are just equal. Therefore, my moment A is 900 over 7. which is equivalent to 128.57. Okay, let's solve everything before we will compare with our answer of CDM. Okay, so that's it. So that is the moment at A, 900 over 7 or 128.57. Okay, I will try to input it in the original figure. So now, summation horizontal, of course, there are no horizontal force at point A, so AH is 0, so AH is 0. And then summating vertical, AB should be equal to BAC, which is 375 over 3, that is 53.57. Okay, again, where did we get these ones? We get that one from your end moments, and shear we transfer this one on the support or on the point. So these are now the support reactions at point A. Moment at A, horizontal reaction at A, vertical reaction at A. So we have that one completely. Now go to your C, support C or point C. Transfer the end moment in this member and also the end moment at that member. You should do that since there are two connected. Or for example, in frames, there are three members connected, so you need to transfer all of the end moments of the three members connected to that point. So these are only two, so these are your MCA. Reverse the direction, BCA, so reverse, MCE, reverse, BCE, reverse. Okay, now these are all transferred in your point C. So at joint C, summate vertical, since actually we only need there your vertical reaction CB. So you will end up there positive CB, going down or negative. So CB is BCA V plus BCE. So that will end up positive 1020 over 7. So that is 145.71. And then, of course, go to point C. That is the reaction at CB. Okay. Go to point C. There is no moment. By the way, if you will try to summate moment here, as I've said, that should cancel out because there should be no moment at C. And yes, because CA and CE, again, if you try to go there, CA and CE are the same but opposite sides. So if I will summate, that should be 0. Okay, so let's go to last point C. Summate there vertical since there are no moments, and horizontal, so we only have there EB, which is equal to BCE, 285 over 7, 40.71. So these are now the reactions, okay, in your indeterminate beam. Okay, this is actually indeterminate to the second degree, but we do not care about the indeterminacy. Okay, we do not care about the indeterminacy in your slope deflection method. So that's it. That is how we will solve, or again, once you have already your support reactions, you can draw your loads. Of course, you can draw your shear and moment diagram, making use of that. And other, it depends on you what method of deformation you want to use. You can solve any deflection or rotation in any point, since you already completed the forces. So you can draw your shear and moment diagram, solve your deflection rotations in any point you want. But actually, you already know your rotation, and we can actually get your rotation and deflection at the support, since in the first place that is the first thing that we solve, isn't it? Theta C and theta E, since that is the only unknown. Those are the only degrees of freedom. Since in the first place, delta are known to be 0 in all of the supports. And then the rotation at this A is 0 since that is fixed. So the only unknown is rotation at C and E. So all we need to do is go back here to your theta C, theta E. Substitute your value of E and I. You will have the numerical value of theta, which is actually a unitless, or that is in radians. It is an angle in radians. That is your theta C, theta E. By the way, why is it positive again? Theta C is positive. Go back. Okay. Considering your theta C tangent at point C, that is this one, get the angle going to the original beam orientation, that is counterclockwise. So that is, wait. Theta C, ISS. That is from the beam to the tangent, which is clockwise, isn't it? So that is positive. And this one is counterclockwise. Theta E is negative, isn't it? Counterclockwise. So go from the original beam to the tangent, that is counterclockwise. Okay. So that is counterclockwise, therefore it is a negative. So all you need to do is substitute your E and I. Substitute your E and I, you will end up there with the values of your rotations, which are actually the unknown. But the thing here is that if the unknown rotations or deflections are within the span, not on the support, then you need to make use of your methods of deformation, which is, again, moment area method, conjugate beam, or virtual work method. We already discussed all of this, or that's already discussed in your theory 1. So again, that is how we will analyze indeterminate beam or continuous beam using your what do you call this one? Slope deflection method. Okay, slope deflection method. So before we will end this unit, okay, I want to review your important concepts. So again, these are the important concepts. This is actually comparing CDM and SDM, the concept behind CDM and SDM. So in CDM, or that is the consistent deformation, the known deformations, or once we know that theta is 0 or delta is 0, that is what we are going to use to formulate compatibility equations, wherein we will use this compatibility equation to solve for redundance. Okay, so that is what is stated in the first sentence. Okay, known deformations, theta is 0, delta is 0, we will use that one to formulate compatibility equation to solve for redundance. Once you have your redundance, bring it back, solve for the rest, okay, of the restraints. In your slope deflection, this is our topic today, your SDM. We are now using the unknown, okay? We are using the unknown deformations to solve for the member end moments. Okay, how is that? Your unknown deformations will serve as your variable to create your slope deflection equation to be used in your equilibrium equation. Once we know your deformations, get your end moments, and then calculate the reaction. Okay, so we are just following the procedure. Okay, identify your unknown deformations. These are your degrees of freedom. Create your SDE, slope deflection equation. Create your equilibrium equation, and then solve for the variables, which are your degrees of freedom, and then go back to your SDE, solve for the end moments, and then use that one to solve for the reactions. Of course, using the end moment, solve the end shears, and then solve for the reactions. Okay, so that is the difference of CDM and SDM. Okay, another important concept is that consider a sign convention in determining your FEM. So as I've said, just like in our example, I consider that clockwise is positive. So I need to stick to that. So whatever now the end moments that will be positive, that is clockwise, since that is my assumption. Therefore, the negative end moments, since in FEM, the negative there is counterclockwise, so the same thing in your end moments, a negative is counterclockwise. Okay, so we will follow that one in member end moments. Okay, so that is your unit 1, SDM of continuous beam. So thank you very much for watching. If you have any question, comment below, or we will discuss that one on the next live meeting. Okay, so thank you very much.